Today we're going deep, like way deep, into a research article called Basics and Recent Advances in Peptide and Protein Drug Delivery. And lucky for us, we have an expert here to help us break it all down. Trust me, some of the stuff they're developing is mind-blowing.
It really is fascinating.
So, peptides and proteins, why are they so special? What makes them so different from the drugs we're used to?
It all comes down to precision. Peptides and proteins can target specific molecules in the body. Think of it like a guided missile.
Wow, okay, a guided missile, much more accurate than traditional drugs.
Exactly.
Less collateral damage, fewer side effects. That's pretty amazing.
That's the goal, absolutely.
The article actually has this table listing all these different peptide therapeutics, and it's crazy to see the range. Insulin for diabetes, of course.
Everyone knows that one.
But then there's etanercept for rheumatoid arthritis, and even salmon calcitonin for osteoporosis. It's wild.
Yeah, and there's so many more in development. The potential is huge.
Okay, but here's the thing. If these things are so amazing, why aren't we all using them? It can't be as simple as just popping a pill, right?
Unfortunately, not yet. That's the big hurdle with peptides delivery. They're fragile, easily broken down, especially in the harsh environment of the digestive system.
Right, so it's like sending a delicate package through a war zone.
That's a good analogy.
Imagine the human body as this intricate landscape, and these peptides are trying to navigate their way to a specific destination. What are some of the major obstacles they face? What are the enemies they have to fight along the way?
Well, first they got to get past the stomach. Highly acidic environment. Like the first line of defense designed to break down food, but it can also wreak havoc on peptides.
Makes sense. Got to get through that acid bath first.
Then there's the army of digestive enzymes in the gut, specifically proteases, that are designed to chop up proteins. The article even calls this collection of enzymes the human degradome.
Whoa, 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 hold on. Human degradum. That sounds intense. I'm going to need a little more explanation on that one. What exactly is a protease, and why is this degradome such a big deal for peptides?
A protease, put simply, is an enzyme that breaks down proteins into smaller pieces. And our bodies have, get this, hundreds of them, each with a specific role. Degradome is just the term for the whole set of proteases in an organism.
So for a peptide trying to make its way through the gut, this degradome is like a major threat, right?
It's like running a gauntlet.
Yeah, like
Okay.
all these tiny assassins are trying to take them down before they can even reach their target. So if we're sticking with that war zone analogy, how are these peptides even surviving? What kind of strategies are scientists using to help them make it through this treacherous journey?
Scientists are coming up with some incredibly creative solutions. One approach is to actually modify the peptides themselves, make them tougher, more resistant to degradation. Think of it like giving them armor to withstand the attacks.
Okay, armor plating the peptides, I like it. But what kind of armor are we talking about here?
One technique is called cyclization. They basically bend the peptide into a circle, make it harder for enzymes to latch onto and break it down. A good example is cyclosporine, that drug they use to prevent organ rejection. It's cyclic, so it's surprisingly effective when taken orally.
So they're using the peptide's own structure as protection. That's pretty cool. What other modifications are they making?
There's pegylation, that's a big one. They attach these long, flexible chains called polyethylene glycol to the peptide. It's kind of like adding a slippery coat of armor, making it harder for enzymes to recognize and attack.
I love it. It's like giving them a disguise so they can blend in.
Exactly, like nothing to see here, move along.
But wouldn't those extra chains make the peptide bigger?
Yeah.
Harder to get where it needs to go?
It's a trade-off. But pegylation also helps with solubility, which means the peptide can travel better in the bloodstream. The article mentions that it's been used to improve salmon calcitonin, the drug for osteoporosis.
So multi-purpose tool, protection and better delivery all in one. Any other modifications? I mean, they must be getting really creative with this.
They are. They're even replacing some of the natural amino acids with their mirror image forms. It's like a secret code the body can't crack.
Wait, what? They're changing the building blocks of the peptide itself. That's brilliant. They're outsmarting the enemy at a fundamental level. Are there any other approaches besides modifying the peptide itself? I mean, it's a war out there.
Well, another tactic is to target the enemy directly. Those pesky proteases.
Okay, I see where you're going with this.
Yeah.
Using those enzyme inhibitors, right?
You got substances that block the action of those protein-degrading enzymes.
So basically sending in a specialized team to disarm the enemy's weapons. Do you have any examples of what they're using for this?
Sure. Soybean trypsin inhibitor, naturally found in, you guessed it, soybeans. And then there's aprotinin, originally used to reduce bleeding during surgery. Both of them block certain types of proteases.
So they're using both natural and synthetic compounds. Fascinating. But what about getting the peptides across that intestinal wall? It's not just about surviving the digestive enzymes, they got to actually get absorbed into the bloodstream, right?
You're absolutely right. The intestinal wall is a tough barrier, carefully controls what gets through, but scientists have figured out some, let's say, creative ways to overcome that hurdle too.
I was just thinking about that. All right, let's hear about those sneaky agents you mentioned earlier, those absorption enhancers. How do they work?
One approach is using substances that can temporarily open those tight junctions in the intestinal wall, just enough to let the peptide slip through.
Okay, now that sounds a little risky. How do they do that safely?
Very carefully. It's about controlled amounts and not disrupting the normal function of the intestinal barrier. The article mentions a few examples. Chatosan, it's from shellfish, and also medium-chain fatty acids. Those are found in certain oils.
So they're using substances that interact with the intestinal wall in specific ways to create that temporary opening. Very cool. But I also remember reading about using a toxin from cholera bacteria. Now that one sounded kind of scary, to be honest.
I get it. But remember, they use it in tiny, controlled amounts. It's been shown to be safe in these contexts. It's called ZOT. And it targets the proteins that form those tight junctions. Just loosens them up a bit so the peptide can sneak through.
So using the enemy's weapon against itself, but in a controlled, beneficial way, that's incredibly clever.
It really is. But they're not stopping there. Scientists are also developing sophisticated delivery systems. Think of them as vehicles. They protect and transport those precious peptides.
All right, let's dive into that. What kind of vehicles are we talking about?
Well, one example is nanomulsions. Tiny droplets of oil and water, like miniature submarines ferrying their cargo through the body. Then you have liposomes, microscopic spheres that mimic cell membranes.
Okay, so we've got stealth submarines and undercover agents. What other options are in the fleet?
Can't forget about nanoparticles. Those come in all shapes, sizes, and materials. Some are even made from carbon nanotubes.
Carbon nanotubes. That sounds seriously high tech. Wow, so much amazing technology is going into delivering these tiny molecules. It's incredible. But what about those other routes of administration, like through the skin, for example? That's got to be a whole other challenge.
You're absolutely right. Transdermal delivery, getting peptides through the skin, that's another exciting frontier. But it comes with its own set of obstacles and some pretty ingenious solutions.
Well, let's hear it. Tell me more about what they're doing to conquer that skin barrier and get those peptides directly into the bloodstream.
You know, the skin really is a tough barrier. It's designed to keep things out, and that includes big molecules like peptides. But scientists, they don't give up easily. They've come up with some amazing ways to get past the skin's defenses.
I love that. Persistence is key when it comes to scientific breakthroughs. So tell me, what are some of the strategies they're using for this transdermal delivery challenge?
One that's becoming really popular is microneedle technology.
Microneedles, right. I remember reading about those. They create those tiny channels in the skin, don't they?
Yeah.
But doesn't that sound kind of painful?
That's the thing. They're so small, they don't actually reach the nerves or blood vessels, so it's painless. You can coat them with the peptide drug, and it just diffuses through those microchannels. Or you can even make them biodegradable, so they release the drug as they dissolve.
Wow, that's pretty cool. So it's like a stealthy, painless injection. Amazing. Are there any real-world examples of this technology?
Oh, definitely. The article mentions Osuno Pharma. They're developing a microneedle patch to deliver peptides and vaccines. And there are a bunch of other companies working on similar tech. It's a really hot area right now.
Sounds promising. Microneedles might just be the answer. But what about other methods? Any alternatives to those tiny needles?
For sure. Scientists are exploring all kinds of options. There's thermal ablation, which uses heat to create temporary pathways in the skin.
Yeah, I remember that one. But I have to admit, using heat on the skin sounds a bit intense.
Don't worry, it's super precise. They use really short bursts of heat, just long enough to disrupt the barrier without causing any damage.
So it's like opening a tiny temporary door for the peptide.
Exactly. Targeted and effective. And then you have electroporation, which uses electrical pulses to increase skin permeability.
Now that one sounds straight out of a sci-fi movie. How does that even work?
It's actually pretty cool. Those electrical pulses mess with the lipid structure of the skin, creating temporary pores, so the peptide can get through.
So it's like zapping open a pathway with electricity. I'm starting to see a pattern here. We've got microneedles, heat, electricity. They're pulling out all the stops to get these peptides across the skin. What other methods are they working on?
There's sonophoresis, which uses ultrasound waves.
Ultrasound, like they use for pregnancies.
Yep, the same idea. But in this case, those ultrasound waves make tiny bubbles in the skin. Then those bubbles collapse, and create microchannels.
So it's like using sound waves to kind of massage the peptide into the skin. That's a cool visual.
And there's iontophoresis, which uses a mild electric current. It works for peptides that have a charge. It kind of drives them across the skin.
So they're harnessing the peptide's own electrical charge to help it penetrate. Clever. It's amazing how many different approaches scientists are developing for transdermal delivery. It really shows their dedication to finding solutions. But hey, let's switch gears for a second. Remember those other strategies like modifying the peptides themselves to make them tougher? I want to make sure we really dive into how they armor up these peptides for that journey through the body.
Good point. It's worth revisiting those modifications. Remember, peptides face a ton of challenges, both in the gut and in the bloodstream. These changes can really help them reach their target.
Okay, let's start with cyclization. We talked about it briefly before, but why is it so effective?
Cyclization is all about making the peptide tougher by basically joining the ends together, like a loop. It makes it much harder for those enzymes to grab on and break it down.
So it's not just about protecting the peptide from the proteases in the gut, it helps in the bloodstream too.
Absolutely. The bloodstream has its own set of challenges, enzymes that want to degrade those peptides. The cyclic structure provides protection in both environments.
The article specifically mentions cyclosporine. Any other examples of cyclization working well?
There's octreotide. It's used to treat certain tumors and conditions like acromegaly, and its cyclic structure is key to its effectiveness.
It's pretty amazing that something as simple as changing the shapes can have such a big impact.
It really is. And then there's pegylation, another really important tool for protecting peptides.
Remind me, how does pegylation work again, and why is it so effective?
So with pegylation, you're attaching those long, flexible polyethylene glycol chains. It's like wrapping the peptide in a shield, making it harder for those enzymes to recognize and degrade it.
It's like giving them a cloak of invisibility.
Exactly. And as we mentioned before, it also improves solubility, helping it travel in the bloodstream.
I remember. It's like a multi-purpose tool. It seems like pegylation has really changed the game for peptide drug delivery. Any specific examples where it's been particularly successful?
One great example is pegfilgrastim. It's the pegylated form of a protein called filgrastim, which is used to boost white blood cell production in chemo patients. Adding PEG means it stays active in the body for longer, so fewer injections.
That's awesome. Makes a huge difference for those patients. It's incredible how these small changes can lead to such big real-world benefits.
For sure. And then there's that really interesting technique of substituting those D-amino acids for the regular L-amino acid.
Oh yeah, that one was kind of mind-blowing. Can you remind me how that one works?
Well, most amino acids in their natural form are left-handed, or L form. By swapping some of them out for their mirror image, the right-handed D form, you basically create peptides that the body's enzymes don't recognize as easily.
So it's like changing the locks on a door and the body's enzymes can't find the right key.
Exactly. It's a pretty brilliant way to protect the peptide.
Like they're speaking a language the enzymes don't understand.
That's a good way to put it. And it's a technique they've used successfully in a number of peptide drugs.
It's amazing to see how they're using their knowledge of chemistry to manipulate these molecules, like playing with the building blocks of life.
It really is a testament to human ingenuity, and it's just the beginning. There's so much more going on in the world of peptide drug delivery.
It's also fascinating. We've covered modifying the peptides, using enzyme inhibitors, enhancing absorption through the gut wall. But what about those delivery systems, those vehicles we talked about?
Right, let's get into those. These are some pretty incredible tools, acting as protectors and transporters for the peptides.
I'm ready to explore this microscopic world. Let's do it. All right, so we're picturing these delivery systems as tiny vehicles transporting those peptide drugs. What are some of the most common types of vehicles?
Well, nanomulsions are getting a lot of attention these days.
Nanomulsions, right. We talked about those earlier, those tiny droplets of oil and water, kind of like miniature submarines.
Exactly. They're like little submarines cruising through the bloodstream, delivering their cargo.
I love that visual. So how do they actually protect the peptides?
Well, the oil part of the nanomulsion, that acts as a shield, protecting the peptide from those enzymes that want to break it down. And since they're so tiny, they can slip through those tiny spaces in the body really easily.
So they're stealthy, protective, and efficient. Sounds like a pretty good delivery system to me.
They really are.
What about those liposomes? Those were interesting. Those microscopic spheres that mimic cell membranes.
Yeah, liposomes are pretty amazing. They're basically tiny bubbles made from the same stuff as our own cells,
Okay.
so they can kind of blend in,
So it's like they're wearing a disguise so the immune system doesn't attack them.
Exactly. They fly under the radar.
Pretty sneaky. And what about those nanoparticles? You mentioned that they come in all shapes and sizes.
Nanoparticles are like the Swiss Army knives of drug delivery.
Okay, I like that.
You can make them from so many different materials, polymers, metals, even carbon nanotubes.
Carbon nanotubes. Wow.
And that means scientists can really fine-tune their properties, adjust the size, shape, surface charge. You can even add molecules that target specific cells.
So they can basically customize the nanoparticle to create the perfect delivery vehicle for each drug.
You got it.
Yep.
Like building a custom spaceship for every mission.
That is so cool. It really seems like the future of peptide drug delivery is incredibly bright with all this amazing research going on.
I think so too. We've come a long way, and I think we're on the verge of some really big breakthroughs that could change how we treat diseases.
I'm really excited to see what the future holds. But before we wrap up, I want to take a moment to acknowledge all the amazing scientists out there working on this. They're tackling some really complex challenges and coming up with some truly remarkable solutions.
I agree. They're doing incredible work.
So to all those researchers out there, thank you. And to our listeners, I hope you've enjoyed this deep dive into the world of peptide drug delivery. It's a fascinating field with so much potential to improve human health.
It really has been a pleasure exploring this topic.
And that's it for this episode of The Deep Dive. We'll catch you next time for another deep dive into cutting-edge science. Until then, keep those curious minds engaged.